welcome to this session on Karnaugh Map simplification. Simplifying a logic circuit is a predominant task in designing digital circuits because simplification is going to yield a better circuit in terms of power consumption and physical process design and in various aspects. There are a lot of simplification methods available. We are going to discuss today on Karnaugh Map simplification. It is a visual or graphical method of simplifying Boolean expressions. So, let us start with a general idea on how to design a logic circuit. So, we are going to see what are the steps involved in designing the logic circuit. So, first we will be given a problem statement. That problem statement has to be converted to truth table and we derive a Boolean expression based on that truth table and we get the final logic circuit for the Boolean expression. So, this is the process involved or the steps involved in logic circuit design. Now, let us take an example. So, we have the problem statement, design a logic circuit to generate gray code. Next, we have to convert this into a truth table. So, this is a truth table for the circuit we are going to design for generating the gray code. This truth table has 4 inputs and 1 output. So, the 4 inputs are represented by the variables A, B, C and D. So, whenever we have 4 inputs in the truth table, we will be having 16 different input combinations and for each of these input combinations we have the corresponding output. Now, here for the gray code generation circuit, the output is high for certain input conditions. Okay. Based on this, we are going to write the Boolean expression. So, before writing the Boolean expression, we have to identify the minterms for which the output is high. What is minterm? Minterm is a fundamental product. So, what is this fundamental product again? Now, in the truth table, we have the input variables A, B, C, D. So, the product of these variables is the fundamental product and here we represent the variable in 2 different forms. One is complemented form, the other one is uncomplemented form. Here we have A prime, B prime, C prime, D, the minterm corresponding to output 1. See, here the A prime represents the value 0, which means the variable A takes the value 0 and the variable D takes the value 1. So, it is not complemented. A, B and C have the value 0. So, we have A prime, B prime, C prime, that is the complemented form and D takes the value 1. So, it is uncomplemented form. Similarly, the next minterm for which the output is high is A prime, B, C prime, D. And similarly, we have the other minterms for which the output is high. Now, next to the minterms, we have represented the numbers. So, these numbers again represent the various input conditions. These numbers represents the various input conditions. So, from this we can write the Boolean expression. So, the Boolean expression is nothing but sum of these minterms. So, the equation 1 y is equal to A prime, B prime, C prime, D plus A prime, B, C prime, D so on is a equation called sum of products equation. Here we take sum of all the minterms for which the output is high. Now, this is the Boolean expression for the given truth table. Now, this equation can also be represented in the second way, that is in the second method where instead of using the variables, we have represented it as M1, M5, M10, M11, M12 and M13. So, this M1 is nothing but minterm representation of the variables A prime, B prime, C prime, D. Okay, it is a symbolic representation. This can be written in a much more shorter way by just using the summation sign. So, here the Boolean function f of the 4 variables A, B, C and D is nothing but summation of minterms corresponding to the numbers 1, 5, 10, 11, 12, 13. So, this is the Boolean expression for the given problem of gray code circuit, designing a circuit for gray code. Now, to design a circuit for this Boolean expression, we need 6 AND gates, and each AND gate should be of 4 input and also 1 OR gate whose input should be 6. It should be a 6 input OR gate. So, if we are going to design a logic circuit based on this, definitely it is going to be a big one. It is not a simple one because we are using 6 4 input AND gate and 1 6 input OR gate. So, we need to use a simplification method to reduce this Boolean expression. So, Boolean expression is required to reduce the number of components and make your circuit less complex. So, what are the steps involved? We have already seen. Now, in that we are introducing this simplification. So, before converting a Boolean expression to logic circuit, it has to be simplified. Now, there are many Boolean simplification methods involved. They are using Boolean algebra, Karnaugh map and tabulation methods. So, in Boolean algebra we have lot of Boolean identities. So, using that Boolean identities we can reduce the equations, we can bring it to a very simplified form, but that is going to be more tedious. We have to remember a lot of Boolean identities and it depends on how we use the simplification. The final result may be little different. So, we go in for the next one, the Karnaugh map or K-map, which is a graphical method, and also we have tabulation method. So, in this session we are going to discuss in detail about the various techniques involved in using the Karnaugh map for simplifying a Boolean expression. Okay. So, what is this Karnaugh map? It is a visual display of fundamental products. It is a table made of squares. Now, each square represents a minterm. Now, how many squares will be there in a K-map? It is given by the general equation 2 power n, where n represents the number of variables. This Karnaugh map was first used in 1953 by the person who devised it. So, it is Maurice Karnaugh. Now, depending upon how many variables your truth table is going to have, we are going to use a corresponding K-map. Okay. So, let us start with a 2 variable K-map. So, we use the variables A and B for the 2 variable representation, and this is a K-map for the 2 variable representation. So, how many squares we have? Just now we saw that for the general formula is 2 power n, where n is a number of variables. So, 2 power 2, 4. So, we have 4 squares in the 2 variable K-map. Now, what is the meaning for each of these squares? Each of these squares represent the minterm. See, we have used 2 variables, A row variable, B column variable. So, the first row is represented by A prime, the complemented form, and the second row is uncomplemented form. Similarly, the first column is B prime and the second column is B. So, if we take the first square, it is a junction of the first row and first column. So, the minterm corresponding to that first box in the table is A prime B prime. Similarly, the minterm corresponding to the second box, that is the box in the second column, first row is A prime B. Similarly, we have the second row, first column, the minterm is AB prime, and the second row, second column is AB. Since it is difficult to remember this in terms of the variables, we use the numbering system. So, 0, 1, 2, 3, 0, 1, 2, 3. Next, we will move on to the 3 variable K-map. So, we will be using 3 variables A, B and C in complemented and uncomplemented form. So, again here how many squares we have? 2 power 3, we have 8 squares. Here the row variables are A and B, column variable it is C. So, the first row is represented by A prime B prime, then second row A prime B, third row AB, fourth row A B prime. Now, see, we have skipped an order when we move from second row to third row. It should be A B prime and the fourth row should be A B generally according to your truth table. But here we are not using that because according to the rule, when we move from one cell to another cell in a K map, only one variable should change from complemented to uncomplemented form or vice versa. So, that is why we have A prime B prime, A prime B, AB and then AB prime in the row representation. So, if you look at the numbers, it is 0, 1, 2, 3. Next we will move to the last row 4, 5 and then one above that 6, 7. So, you should remember this numbering. So, usually this is called gray code numbering. So, this is a 3 variable K map. Next we will move on to the 4 variable K map. This 4 variable K map, you have 16 squares, 2 power 4, 16. You have 4 variables A and B row variables, then C and D column variables. Again first row is represented by A prime B prime, then A prime B, AB, AB prime. Similarly, if you look at the columns, it is first C prime D prime, C prime D, CD, CD prime. Okay. So, when you look at the numbering, it is 0, 1, we move to the last column 2 and then we will come back to the previous one 3. Similarly, we have 4, 5, 6, 7, then we move to the last row 8, 9, 10, 11, then 12, 13, 14, 15. So, each cell in this table is represented by the numbers. So, this is a 4 variable K map. So, we have seen how to represent a 2 variable K map, 3 variable K map, 4 variable K map. We can also have higher order K maps, but in this session we are just restricting to 2, 3 and 4 variable K map. What are the different steps involved in simplification process using K map? Now we have to see how to fill up the K map. So, given a Boolean function, how to fill up the K map. So, throughout these sessions, we will be representing the Boolean function in terms in this particular way, f of a comma b equal to summation m of 0 comma 1. What is the meaning? So, it is a function with 2 variables, it is a Boolean function with 2 variables and the minterms 0 comma 1, the minterm 0 and the minterm 1 have a high output. That is, the output corresponding to minterm 0 and minterm 1 is high. So, we are going to fill the corresponding numbers, with 1. So, in the K map, the position corresponding to 0, the cell corresponding to 0 and 1 is filled up with 1s, the rest are filled up with zeros. So, we have the Boolean function and the function says the minterms 0 and 1 has high output value. So, we fill up the K map with 1 in 0 and 1 position and the rest are filled with 0. So, this is the way to fill up the 2 variable K map. Now, let us see how to fill a 3 variable K map. So, here the Boolean function is summation m 0 comma 1 comma 2 3 5 7. So, what is the meaning? For these corresponding minterms, the output is high. So, these positions in the 3 variable K map is marked with 1. So, 0, 1, 2, 3, 7 and 5 are marked with 1 and the rest are filled with zeros. Yes. So, next we will see how to fill a 4 variable K map. Now, we have a Boolean function of a, b, c, d 4 variables and it says that the minterm corresponding to high output are 0, 1, 3, 4, 5, 7, 8, 9, 11, 12, 13, 15. Now, these minterm positions should be filled with 1. So, in the table, in the K map, we are going to fill those positions corresponding to these numbers as 1 and the rest is going to be filled as 0. So, we have completed in filling the K map according to the given Boolean function. So, we have seen how to fill up a 2 variable K map, 3 variable K map and 4 variable K map when you are given a particular Boolean function. Okay. Now, comes the important aspect of how to do the simplification. Okay. Now, the first step in doing the simplification, we have to identify adjacent ones in the K-map. We have to identify adjacent ones in the K-map. So, these adjacent ones can be grouped as pair, quad or octet depending upon how many ones you are grouping. If you are grouping 2 ones, then you call it as pair. If you are grouping 4 adjacent ones, you call it as quad, and if you are going to group 8 adjacent one, you call it as octet. Now, we will see how to form these groups in the K-map. Now, let us first take a pair, how to form pair with 2 adjacent ones. Let us take the same example which we have already done. So, this is a Boolean function, we have already filled, we saw how to fill the K-map for this Boolean function. Now, we have 2 ones in row 1, we have 2 ones in row 1 adjacent to each other. So, these 2 ones can be grouped as a pair, these 2 ones can be grouped as a pair. Similarly, now in this 2 variable K-map, I have 2 ones. Now, here they are adjacent in the first column. Okay. So, these 2 ones are adjacent to each other in the first column. So, I can group them and make it as a pair. Okay. Next, we will see how to form a quad with 4 adjacent ones. Again, it can be row wise or column wise. So, this is again we are taking the 2 variable K-map. Now, all the cells are filled with 1, all the cells are filled with 1. So, they are adjacent, all the ones are adjacent to each other. So, we are grouping it as a quad, we are grouping it as quad. Next, we go for the 3 variable K-map. So, just look at this K-map, we have 4 adjacent ones in row 1 and row 2. So, these 4 ones can be grouped as a quad. Similarly, in column 2, we have 4 ones. Again, these 4 ones can be grouped as quad. So, in this particular K-map, a 3 variable K-map, we are able to identify 2 quads and they are overlapping with each other. It is okay, it is accepted. Next, we will see how to form an octet with 8 adjacent ones. So, again we take a 3 variable K-map. So, all the cells are filled with 1. So, all the ones are adjacent to each other with respect to row and column. So, we group them as an octet. Next, we will see a 4 variable K-map. So, here I have ones in 3 columns, ones in 3 columns. So, the first 2 columns is going to be grouped, the ones in the first 2 columns they are going to be grouped as octet. Similarly, the ones in the second and third column they are going to be grouped as another octet. Here again we have 2 overlapping octets. Okay. Now, we have seen how to group the ones, adjacent ones in the form of pair, quad and octet. Now, we are going to see how to write the simplified Boolean expression for that particular quad, pair or octet. So, what is the rule we have to follow? So, we have to drop a variable that changes from complemented to uncomplemented form or vice versa when we move from one square to another. So, when we move from one square to another, if any variable changes from complemented to uncomplemented form or vice versa, we have to drop that variable. So, okay, let us go back to our example. So, here we formed a pair, we grouped these 2 ones as a pair. Now, these 2 ones are in row 1 corresponding to the variable A prime. Okay. Now, when we move from one square to the next, we are moving from column 1 to column 2. So, as we move from column 1 to column 2, the column variable B changes from complemented to uncomplemented form. So, we have to drop the variable. According to the rule, we have to drop the variable that changes from complemented to uncomplemented form. So, we are dropping B. So, finally, this pair is represented by A prime. So, this pair is represented by A prime. So, we can easily say that the Boolean expression for this is given as y equal to A prime. So, we have been able to reduce one variable by dropping it. How do we drop it? Because we are able to form a pair or group the adjacent ones. Now, in the next example, so we have already formed a pair with these two ones which are in successive rows, okay? They are in a same column. Now, here the column variable is B prime, the column variable is B prime, and when we move from row 1 to row 2, that is from one cell to another or one square to another, the row variable A changes from complemented to uncomplemented form. So, we have to drop the variable A, okay. So, finally, your y is equal to B prime, y is equal to B prime. So, this is a simplified Boolean expression for this particular problem, okay. Next, we will see how to write an expression for a quad. So, this is again the same example we have already taken. So, here we have two quads, Q1 and Q2. Now, let us take the quad Q1. So, the quad Q1 encompasses ones in the first row and second row, okay. So, if we move from first row to second row, the variable which is changing is B. B changes from B prime to B. So, we have to drop B. Now, also as we move from column 1 to column 2, C changes from C prime to C, that is from complemented form to uncomplemented form. So, C has to be dropped. So, the final expression for quad 1 is, let us say y1. y1 is equal to A prime because the first two rows are represented by A prime. So, let us say y1 equal to A prime. Now, let us take the second quad Q2. Now, this Q2 consists of ones in the entire second column. The second column is represented by the variable C. Now, if you look at the second quad, it involves all the 4 rows. So, as we move from one row to another row, both A and B changes. Say as we move from row 1 to row 2, B changes from complemented to uncomplemented form. So, we have to drop B. Similarly, as we move from second row to the third row, A changes to from complemented to uncomplemented form. So, we have to drop both the variables A and B. Finally, we are left with the variable C. So, quad 2 is represented by the variable C. So, y2 is equal to C. Now, your final equation, the final Boolean expression y is equal to y1 plus y2, which is nothing but A prime plus C, A prime plus C. See, we are able to reduce so many variables and we have got a much simplified expression. Okay. Next, we will see how to write an expression for an octet. So, again the same example where we have two octets. Now, let us take one octet at a time. We will take octet 1, O1. Now, this octet has ones in the first two columns and in all the 4 rows. So, if we go from first column to second column, the variable D is changing from complemented to uncomplemented form. So, we have to drop D. Already we have seen as we move down the rows from 1 to 2, 2 to 3, 3 to 4, both the variables A and B change from complemented to uncomplemented form and vice versa. So, we have to drop both the variables. So, finally, for the octet 1, we are left with the variable C prime, which means octet 1 is represented by the variable C prime, y1 is equal to C prime. Similarly, let us take the octet 2. So, in this we have column 2 and column 3. So, when we move from column 2 to column 3, C is changing from complemented to uncomplemented form. So, we have to drop C and this involves all the 4 rows of the K-map. So, as we move along the rows, both A and B changes from complemented to uncomplemented form. So, we have to drop A and B again. So, finally, we are left with D. So, octet 2 is represented by D. So, we have an expression for octet 1 and octet 2. So, the final equation is nothing but sum of the expression for 2 individual octets. Finally, y is equal to C prime plus D, y is equal to C prime plus D. Okay. Now, just to summarize, so whatever we have done so far, specifically how to group the ones, we will quickly go through these points. A pair eliminates one variable and its complement. So, we have seen that how in a pair when we move from one cell to another cell, a variable which changes has been dropped. So, basically in a pair one variable is eliminated, one variable is eliminated. In a quad we were able to eliminate two variables and their complements. And in an octet we were able to eliminate 3 variables and its complement. So, always it is better to look out for, when you start simplifying a K-map, just look out for the octets first, then go for quads and then go for pair, and if not you are able to find all these, then go for isolated one. That is going to give you a very much simplified equation for you. Next we will move on to another important aspect of this K-map simplification, that is redundant groups. So, when we try to group the adjacent ones as quad, pair and octet, sometimes we form redundant groups. What are these redundant groups? Now, just look at this particular example where we have grouped the ones as pairs and quad. So, first we have a quad, so where we have combined all the 4 ones in the center. Now, to include the ones, the remaining ones, we are forming pairs. So, we are writing the Boolean expression for the 4 pairs and quad. So, we get 5 terms. So, your Boolean expression has 5 terms. But if you carefully look at the quad, you can see that the ones in the quad are already involved in other groups, that is they are involved in ones. So, if you form a quad again with those ones, then definitely it is a redundant group, it is a redundant term in your Boolean expression, it becomes an additional term. So, we do not want to have an additional term. So, we want our circuit to be more simple, our Boolean expression to be of less terms. So, we can remove that redundant group. So, if we remove that redundant group, we will have this K-map where we have only 4 pairs. The rule is we should not leave any ones in the K-map without being used in any of pair, quad, octet or isolated one. So, here we have involved all the ones. Still if we are going to use the quad, it is going to be redundant. So, we can avoid such redundant groups while simplifying using K-map. Okay, next we are going to see another technique in simplification process of this K-map, that is rolling the K-map. Your K-map, the 4 variable K-map, 3 variable, 2 variable, everything, it is a 2D representation of rows and columns, 2 dimensional. Okay. Now, let us take the 4 variable K-map. This 4 variable K-map, imagine it as a sheet of paper. This paper can be rolled along the horizontal axis or vertical axis. So, if you roll the K-map along the vertical axis, then columns 1 and 4, they are going to become adjacent ones. That is columns 1 and 4, they are going to become adjacent. Similarly, if you are going to roll the K-map along the horizontal axis, then rows 1 and 4, they are going to become adjacent. Now, what is the effect of such rolling? So, when we roll the K-map along horizontal or vertical axis, the rows 1 and 4 or the columns 1 and 4, they are going to be adjacent. So, the ones in those corner rows and columns can be grouped again. So, let us see an example of how to roll the map and again get a very simplified expression. Okay. So, let us take this 4 variable K-map. You can see that you have ones in the first column and second column. So, as we have it this way, we can form only pair. We can group them as 2 pairs. But if we can roll the map along the vertical axis, the vertical axis is an imaginary line shown in this particular slide in dotted yellow line. If we are going to roll the map along this vertical axis, then column 1 and column 4, they are going to become adjacent. So, the ones in those 2 columns will become adjacent, so that you have 4 adjacent ones, you can form a quad. So, we are able to form a quad here by rolling the map or wrapping the map. So, this is again is going to give a better simple term. It is going to again simplify your Boolean expression. So, this is another technique of simplifying your Boolean expression in K-map. So, we will see one more example. So, in this example, we can form an octet with ones in both the columns, column 1 and column 2. Apart from that, I have ones in column 1 and column 4. So, if I am not going to roll the map, I can form a pair. I can form a pair and 2 isolated ones. So, I will be left with 1 octet, 1 pair and 2 isolated ones. Okay. But here we can roll the map along the vertical axis. If we roll the map along the vertical axis, then I can wrap these ones in the corners, that is in column 1 and column 4 as a quad. So, I get a much simplified Boolean expression with 1 octet, 1 quad and 1 pair. So, this rolling the map is going to help me to give a much more simplified Boolean expression. Okay. Now, we will quickly go through the steps in K-map simplification. So, enter a 1 on the K-map for each fundamental product that produces a 1 output and rest to be filled up with zeros. Encircle the octets, quads and pairs and isolated ones. You can roll the map and also you can have the overlapping groups, and then if any isolated ones remain after forming this quad, pair and octet, you can have it, you can also encircle it. You can eliminate any redundant group. After doing all this, identify the Boolean expression for each of these groups, and finally it is the sum of all these will give you the final Boolean expression. So, write the Boolean expression by ORing the products corresponding to each of these encircle groups. Okay. We will quickly look at few more examples for K-map simplification. So, this is a gray code expression which we took it as a first example. So, we saw that without simplification for gray code we need 6 4 input AND gates and 1 6 input OR gate. Now, let us see after simplifying what is the requirement for the circuit. So, if we represent this function in the truth table, so we are able to form 3 pairs. We are able to form 3 pairs. So, we get a simplified Boolean expression which has only 3 terms, and each of these terms has only 3 variables. So, if we are going to design a circuit, gray code circuit for this particular equation, we need only 3 AND gates, and each of these AND gates require only 3 inputs, and we need 1 OR gate again of 3 input. Okay. So, now we could see the advantage of using this K-map for simplification. Next, another example. So, I have a Boolean function f of a, b, c, d equal to summation m 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13. So, if I am going to represent this in the K-map, I will be able to form 2 octets. I will be able to form 2 octets. So, we can write the expression for the octets. So, the first octet includes column 1 and column 2. So, column 1 and column 2, C changes, C does not change, C remains as C prime, D changes. So, we can drop D. Along the rows A and B changes, so we can drop A and B. So, the final expression for octet 1 is C prime, and similarly for the octet 2, let us take this example where the Boolean function is represented as sum of m as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13. Now, if we are going to represent this in the K-map, you will have 2 octets. We can group the ones as 2 octets. Octet 1 includes ones in first row and second row. So, when we move from first row to second row, B changes from complemented to uncomplemented form. So, we are dropping B. As we move along the column, so C and D changes from complemented to uncomplemented form. So, we are dropping C and D. So, for octet 1 we have the expression A prime. Similarly, if we take octet 2, as it includes all the octet 2 includes all the 4 rows and the first 2 columns. So, if we move along the 4 rows, A and B changes from complemented to uncomplemented form. So, we are dropping A and B. As we move from first column to the second column, D is changing. So, we are dropping D. So, octet 2 is represented by C prime. So, the final expression is y equal to A prime plus C prime. Okay. Next, another important aspect of this K-map is using don't care conditions. There might be logic circuits where not all the input conditions are required. Certain input conditions are not necessary for designing a logic circuit. So, those input conditions are called as don't care conditions, because for those input conditions we do not mind whatever be their output, whether it is 0 or 1, we do not require the details of the output for those input conditions while designing the circuit. So, we call these input conditions as don't care conditions. Those output can be 0 or 1. So, we represent those output as X. So, X can take either 0 or 1. We will see an example. So, this is a 4 variable truth table where we have indicated the don't care conditions with X. Now, the input conditions corresponding to 10, 11, 12, 13, 14 and 15 are represented with X, meaning those input conditions are not required for designing the circuit, but still we write it so that we can use the X as either 0 or 1 for getting a simplified logic circuit. Now, we will see how to design a logic circuit with don't care conditions. Before that, see the change in the Boolean function. So, f of a, b, c, d is equal to summation m, then plus we have included the don't care conditions also. We have included the don't care conditions also. Now, we will see how to get a simplified Boolean expression for this. This K-map is a representation of the previous truth table. So, here you could see the X values, the don't care conditions along with 1. So, we have to group the 1 here. So, the 1 in this is grouped along with the X adjacent X values. So, here we are treating the X values as 1. As we said earlier, the X can be taken as either 0 or 1 just to make a group or form a group with this 1, we are treating X value as 1. So, we are able to form a quad. The remaining X values are treated as 0. So, for this particular K-map, we are able to get a Boolean expression y is equal to AD corresponding to the quad. So, we are able to achieve this by making use of the X, 3X adjacent to 1, where these 3 X values are treated as 1. So, we are able to form a quad. So, this is the advantage of using the don't care condition. Let us quickly go through the ideas about don't care conditions. So, if we have ones, zeros and don't cares, just fill up the K-maps, then encircle the actual ones on the K-map in the largest group you can find by treating the don't cares as ones. And after the actual ones have been included in groups, disregard the remaining don't cares by visualizing them as 0. Some more examples. So, we have a Boolean function of 4 variable minterm, summation minterm for 7 plus the don't care conditions. So, we can represent it in this form in the truth table, where I have X in the third row, then fourth row, and I have one single 1 in the second row, third column. Now, this 1 can be grouped with the X. This 1 can be grouped with the X to form a pair. So, the expression corresponding to that is BCD. So, just to show that the ones can be grouped with x values and we can form a simplified expression, Boolean expression. So, this is another example. We have one more example. So, here again you have the min terms. So, this is a Boolean function, summation m is 10, 11, 12, 13 plus don't can conditions in 0, 1, 2, 3, 4, 5. So, we are going to fill the K map for this particular Boolean function. After filling up the K map, we have to identify the groups. For identifying the groups, we are going to include the x values which are adjacent to ones. So, here we are able to form a quad. We are able to form a quad by treating those two x as 1. So, we are able to form a quad. Similarly, we can wrap this particular map along the horizontal axis, so that columns 1 and 4 they are going to be adjacent, so that we can form a quad with the 2 ones here and the 2 don't care conditions. See, we should remember we cannot form groups only with don't care conditions. Any group you are forming, either it is pair, quad or octet, it should have at least single one along with x. So, any grouping with only x values is not allowed. Similarly, any grouping with only zeros or any grouping even with 1 0, it is not allowed. So, it should be groups formed with adjacent ones. So, after simplifying, we get a simplified Boolean expression for each of the quads, So, y is equal to b c prime plus b prime c. So, we have seen more examples on how to use K map for simplifying the Boolean function. So, we will just quickly recap what are the steps we need to follow. Given a Boolean function, so we have to represent that in the K map. For that, first we have to see how many variables are given in the Boolean expression. The Boolean function might be 2 variable, 3 variable, 4 variable. Depending on that, choose a K map. After choosing the K map, fill up the K map with ones and zeros in the corresponding min term positions. Then try to form groups of pair, quad or octet. Try to form groups with the ones. After forming the group, identify the expression for each of the groups and finally or all the expressions. So, you will get the final Boolean expression which is in a reduced form. Okay. And in this we have to look out for overlapping groups, redundant groups. Redundant groups have to be removed and we should not include zeros in any of these groups, and then all ones in the map should be included in any one of the groups. Hope this becomes an easier process to do the simplification, and we have done a lot of examples. So, you can work out more examples, so which will make your simplification process much easier. Thank you for listening.